Welcome everyone. My name is Joshua, and I'll be talking about Bedrock, sort of why we're doing it, what it is, and then kind of work from a very high level down into a very technical level. So yeah, this is the talk. What is it? Why are we doing it? Again, high level, low level, some differences, and then we'll probably actually skip the exercise. But there's a DevNet. You can join it if you want. So at a very high level, it's a redesign of the Optimism rollup to utilize Canon and increase reliability. That's like the one sentence how I would describe it to anyone. And so why do this? So there's the two parts, the Canon and the reliability. On the Canon side, Norswap will be talking about this later. He had a short talk at ECC as well. But it's basically a generic optimistic fault-proof backend. So what you have to do is you just set up your code to be deterministic, not quite fully stateless, but based on kind of pre-image oracle. So once you set up your system in this way, you can just compile it to MIPS and then run an interactive game over it. And this works with any code that you compile. So if you want to update the EVM, update something inside Geth, it becomes really easy to deploy these upgrades because you just take it, recompile it, put it on chain, and distribute it to your kind of node operators the same way you do any hard fork. So that's one of the benefits of Canon. It turns out being generic actually works a lot better than being specific, because the current thing we have is we have our custom L2 execution engine. So this is Geth in Golang, and just executes transactions. And then we have contracts on L1, which exactly match that execution. So keeping them in lockstep takes a lot of work. Takes a lot of work to get upgrades. So we're migrating over to Canon, and then Bedrock is the roll-up tech that lets us use that. And then kind of on the reliability side, there's a bunch of different things, but we'll kind of explain more of this later, but we'll be able to just take SnapSync from Geth and from kind of the ETH2 architecture. And if you've ever actually operated an Ethereum node, you know how nice SnapSync is. We'll have a TX pool, we'll propagate blocks around, just a lot of other stuff. It'll be a much smaller diff, it'll be easier to audit, and then again, a lot easier to stay up to date with Geth. Because Geth actually changes at a pretty rapid pace. So you have to really stay on top of that. Cool. So that's the why we're doing it, and we'll go through a very high level system overview. So the first main component of this system is the rollup node. So this is comprised of the OP node, which serves a function similar to the consensus client in ETH2. And as well as the L2 execution engine. So this is just the thing that reads data from L1 and then creates the L2 blocks. Uses the Ethereum engine API, so you can sub out a different execution engine without really many changes, as well as kind of get have the direct L2 execution engine to direct L2 execution kind of sync. And then there's actually also a peer-to-peer network on the rollup node side, and so that enables unsafe block distribution. I'll explain that a bit more later, but that just means any replica can just join the network and have a very up-to-date view of the chain. And then yeah, with this architecture split, you really simplify the execution engine. And so now here's basically just a diagram of this. So this is the dividing line between kind of the rollup node and your L1 node. And so from the OP node right now, we only talk to the L1 execution engine. Maybe we'll talk to the beacon client with 4844, but you just kind of abstract it away as here's my L1 data, and then it gets processed through the rollup node, and then kind of gets executed on your L2 execution engine. Here's another diagram showing how it mirrors the ETH2 architecture, and something kind of we're like heavily leaning on, and we think it really simplifies things. Cool. Now, that's the one specific node and part of the system. Now, kind of taking a step back, they're not the only actor in the system. So the sequencer and the verifiers, those are both OP nodes or rollup nodes. The difference is the sequencer actually produces the blocks, and the verifiers just kind of like check the blocks and maintain their own local view of the state. Then we have the batcher, which is responsible for submitting the data to L1. This is the component that ensures the data availability. Then we have the proposer, which submits L2 state roots. This is the component that enables withdrawals on L1. And then kind of the last one that's not ready yet is the challenge agent. This is the piece of software that looks at the output proposal on L1 and says, is this correct or not? And that will be part of Canon. That's kind of the fraud-proof game. So right now we have the rollup node, the batcher, and the proposer already, and kind of working through dev nets there. And there'll be test nets later this summer. So here it is in diagram form. Yeah, your sequencer and verifier here as the rollup nodes, reading from L1, talking to each other in the peer-to-peer network. And then you can see here that the batcher reads the new blocks from the sequencer, submits them to L1, and then the output proposer looks at the verifier's execution and the state root, and then submits it to L1. And then your challenge agent works off the verifier in L1 to play that game. And then kind of your two entry points are onto L1 or to L2. Cool. So I'll pause here. If anyone has questions, there's going to be a lot of opportunities for questions through this talk. Yes?
Are sequencer and batcher the same actor? Are they the same entity, the same software?
So they are not the same software, but they are the same. With the current trust model, they're very similar and basically the same. Long term, they're going to be split out. I mean, there are different binaries. Long term, they're going to be split out into like different roles with like different trust assumptions, and then that's kind of part of the longer term decentralization thing. Yeah, good question.
Can you go back for a second?
Yes.
Okay, and now can you go to the next step? So my question is, the L2 user would read the data directly from the sequencers or verifiers?
So you would be talking to a verifier. So the flow for like to get the L2 chain tip, the sequencer produces the blocks, gossips them out to the verifiers, and that's how you would kind of see your transaction get included. So yeah, so like your block explorer infra providers would be running verifiers with this peer-to-peer connection.
So
Yes.
the user does not interact with sequencer at all?
Not really.
Directly?
Yeah, so the plan is we're gonna have a mempool, and so kind of like we'll basically probably have a ring of verifiers around the sequencer, because the sequencer is like the one entity that produces blocks.
Is this the current architecture or the future one?
Future.
It's the same kind of question. Like people, I think, are familiar with the idea of submitting transactions to the sequencer. Like, can they still, or should they not? Can they not?
Because I don't really think of it as like submitting it to the sequencer, because now you do have this mempool and you have this peer-to-peer. So it's like I guess you could, if we opened up a direct connection, like the same way you could submit to a miner, but I don't think we'll have much of that, maybe, but conceptually it's just like dump it in the mempool.
So will it increase like this soft finalization time? Like, it's very snappy now, right?
Yes. I don't think it would change it that much. We'll talk about kind of the block times later, but it's going to be a 2-second block time. And then that's still going to be very fast from a user perspective. And with this network, I don't think the mempool latency is going to be that high.
So one more.
Of course.
So is it likely that a sequencer entity will run a sequencer in kind of like a private IP area and like a verified and public IP area and just like expose one API to end users?
I mean, if that's how I was personally doing it, yes, that's what I'd do. I wouldn't expose the sequencer publicly, but you could have a ring of verifiers around it really easily, and it just kind of passes through without a problem.
Are there any like DOS like attack vector there? If someone just DOS the sequencer, you would expose the public?
Yeah, I mean, that's why you'd put verifiers on the outside.
So meta enough, I think the mic probably doesn't pick up the question, so for the recording.
Oh, yes,
I'm not
sorry.
gonna say the question again.
Yes, try to repeat the questions. Cool. Awesome. Yeah, we went through the questions. Yeah, I put a lot of question slides just to remind everyone that please ask them. Okay, so now we're gonna go through some of the data flows. So the three most common are going to be deposits, L2 transactions, and then withdrawals. So for deposit, this is how you mint L2 ETH. This is how you kind of bridge money over. This is how like the canonical bridge utilizes the deposit mechanism. And it actually is like a fully generic message passaging system that basically can execute transactions on L2. So you basically send a message to the L1 Optimism portal contract or deposit contract. That contract holds the ETH that you mint on L2. It does some fees for the users, and then it emits an event. And then on the L2 side, the nodes read the event, recreate the transaction based on the event, and then execute the transaction. And then this all happens very fast. Within a couple blocks of it being submitted on L1, it's going to show up on L2.
The sequencer will do that?
Every node reads deposits from L1. Yes. And so now we have L2 transactions. This is your most typical transaction. You just send it off to the L2 transaction pool. Sequencer sees the transaction and includes it in a block. Then the batcher takes that new block, transforms it into a batch, submits it to L1. And then once it's on L1, replicas as well as the sequencer actually read the batch and kind of create the chain. Yeah, so L2 side, back to L1 side. And then the withdrawals. So on L2, you initiate a withdrawal to the withdrawal contract, and that burns the L2 ETH and kind of makes a commitment inside the L2 state to the actions of the withdrawal. So it's like how much ETH was burnt, and then also like who the sender is, and like you can actually basically relay a transaction from L2 to L1 with this mechanism. So you can have it like, it saves like message.sender. So if you have a bridge, or like a contract or bridge on L2, you know that it could like authenticate itself basically, and then you can have your contract data, and that all gets saved. And then on L1, once that's from L2 you emit the event and like save everything, and then on L1 you proposed the output of that, the state root, which includes that commitment because it's in the state. You wait the challenge period to make sure that it's a valid output commitment, and then finally you can execute the withdrawal on L1. And that's done through basically providing the data from the event. You hash it, verify that the commitment is correct, provide that proof, and then from there it executes the transaction on L1 and gives you back your ETH. So that's the withdrawal flows. And we have a question slide. Cool. Go ahead. So now comes the nitty gritty. We're basically going to go through these same flows, except with just even more detail. Just basically high level down to really low level. And we'll kind of explain like, not just like, okay, there's some data here, so there's data there, like when the data has to be included and how it is. So at the very base of the system, this is the Optimism portal deposit contract. As we said, this holds all of the ETH bridged onto L2. With our canonical bridges, it doesn't actually hold ERC20s. That's kind of held in like an outer bridge. But the canonical bridge does use the deposit contract. As I said, it's arbitrary message calling. Here's your deposit event. Some of the trickier things kind of when using it is you don't actually get a gas refund on L2 because you're buying gas on L1, and there's kind of a fee market around that we'll go into. And then also, it's really easy to send ETH onto L2 now. Like you just send ETH to the contract, and it'll do all of this deposit event for you and send it to you on L2. And so we're going to set up an ENS for that. So it's exciting for us to make it really easy to get ETH onto L2 from any wallet, even without integrating the wallet. And so here's more details of the fee market on L1. So we have a 1559 style fee market on L1 for deposits, and then actual 1559 on L2. And those are actually two disconnected fee markets. It's very hard to transfer information between L1 and L2 in kind of a timely manner. So you just, as you kind of have deposits, and there's a target gas limit for deposits, and if there's more demand for deposits, the deposit gas price goes up. If there's less demand, the target gas price goes down. Pretty simple. And then if there's more demand for deposits than gas allocated to deposits, we revert to the first deposits inside the L1 block get the priority. And that's also deposits are always executed at the start of an L2 block, and they have the same order as on L1. So there's still a little bit of an element of a PGA for deposits here, but typically you'll get it through just like the 1559 base fee adjustments. Yep, and you just pay your fees with a gas burn. It's pretty much the same as now. And then there's a little bit of a credit for the computation done, but it's not fixed. And you'll just kind of like send a transaction to the contract, and it'll figure out how much your gas is. Yeah.
What's the target amount of maybe for gas?
Yeah, what's the target amount for gas? We haven't finalized those parameters yet. So the target's probably going to be in the couple million range of gas. The maximum's going to be larger. Yeah, somewhere in there. Those limits will be less than kind of the L2 limits, though, because we do include gas from the deposits in the L2 blocks. Yes?
Why do you have to transform the address of the deposit if the caller is a contract?
We have to include the address on the deposit if the caller's a contract? Or?
If the caller of a deposit transaction is a contract, there is some aliasing.
Oh, yes. The aliasing, that's because you can end up with, I think you can end up with addresses on L1 and L2 that are different contracts, and we're trying to keep that separate. It's kind of my best understanding of that right now.
Yeah, if you have the same, you have contracts with the same address on L1 and L2, but two completely different bytecodes, and so they're not the same contract, and you can't treat them as the same contract.
Yeah.
So aliasing is a sort of cheap way of namespacing addresses.
Yeah. Yeah, that's it. Yeah, and there is that step in deposits. And I believe we already have that, right, Kelvin? We already do the aliasing. Yeah. Yeah, so this is something that's staying the same from the current system, it's aliasing. Cool. So once all these deposits are done, we then go to the sequencer, which is constructing blocks. It reads data from the deposits as well as from its L2 mempool. And then we'll get to a diagram here, each L2 block references back to a specific L1 block, and you have multiple L2 blocks per L1 block, because the L2 block time is probably about 2 seconds. L1 block time is 12 to 15 seconds. And then the very first, so all of the L2 blocks belonging, which point back to a specific L1 block, we refer to that as an epoch. So these two blocks are an epoch, these two are an epoch, and so here these two refer back to L1 block number 2, and so that's kind of the group. And so this very first block of the epoch, that is the block that has deposits from that specific L1 block, and you have to include deposits in that specific L2 block, and then the first way we enforce deposit inclusion is through the sequencer drift. So this means that the sequencer has to, each L2 block has a timestamp, and it can't have an L1 origin with a very old timestamp. So over here, it can't decide to instead of like pointing to L1 block 2, it can't decide to point to L1 block forever, the block number 1 forever. Eventually it must switch over to block number 2, then eventually to 3, and then eventually to 4. And because deposits must be included in the block, it can't censor deposits, and it can't even kind of temporarily censor a block, temporarily censor a deposit for more than the sequencing window. So this is one of the 2 liveness mechanisms for deposits. Yeah, reads from the mempool, and then very similar to now, it charges an L1 availability fee based on the bytes of the transaction, and then how much it actually costs to submit the transaction on L1. That's the sequencer. And then for the verifier, it just reads deposits in the exact same way, but now it also reads batches from L1 and then reconstructs the rest of the blocks. And so then here we have the second mechanism to enforce liveness even when the sequencer is down. So it has this concept of a sequencing window, and it only looks for batches inside the sequencing window, and if there's no batches submitted inside that window, it just creates empty batches. And so if the sequencer is fully down, you can continue to produce deposit-only blocks. And then, yeah, the diagram will explain it a bit better, but you have these windows overlap, and they're from the L1 origin to the L1 origin plus the window. These windows overlap, and then because of some of the rules, we don't actually have to wait the entire window, but if the sequencer's down, you do. So it's yet another optimistic mechanism. We like those. All right, so the sequencing window. So here, block 1, so you look at 1, 2, and 3. Here, the L1 origin, the window size is 3. Here, the L1 origin is 2, so you look at 2, 3, and 4. And that's how the sequencing window works. Any questions on this? So now we get to talk about these red blocks, which are the unsafe. Oh, Liam?
What's the right way to think about the selection of the sequencing window? Like why would I want to increase it or decrease it?
So increasing the sequencing window gives you more time to submit batches, which means you could have a little easier time operationally. You could wait until the L1 price goes down. Having a very short sequencing window means that your system is very live, and if it goes down, you'll just like fall back to deposits. So those are kind of the 2 trade-offs. And now with eager batch derivation, you're kind of running at the speed of the batcher. And then really the sequencing window is important for like, if you're like a high trust user and you like you want to make sure the data is never going to be changed, that's where you like have to rely on L1 rather than the unsafe blocks. Yep.
Could the sequencing window be dynamic based on like congestion of L1?
There's a world, could the sequencing window be dynamic? There's a world in which that's possible. It's probably going to be a ways away. Cool, so unsafe blocks. So kind of touched on this just a tad. A safe block is a block fully derived from L1. So if you're like an exchange, this is what you trust. And then you can even track like how far back the last L1 block that modified this L2 block was. And so that's where you get your safety. And then there's unsafe blocks, not fully derived from L1 blocks. So the moment you create a new block on L2, it hasn't been submitted to L1. So it's probably going to be submitted and it's probably correct, but it hasn't fully been submitted yet. So with these blocks, we still gossip the unsafe blocks around because they're probably correct. But as we read data from L1, we check our unsafe blocks against what we derived, and then we always favor what we derived. Verifiers do this, the sequencer does this. Actually, it also works well to handle L1 reorgs. Yeah. And so this is kind of like the strong safety mechanism. And then, yeah, here, because the sequencing window hasn't passed yet, maybe the batches aren't there yet, you have these unsafe blocks, which haven't been fully verified, but they exist, and you can kind of still work with them. Yes?
How many reorgs can we expect?
How many reorgs can we
How
expect?
often?
How-
How deep?
Yeah. So there's two things that would cause reorgs. The first is if the batch submitter or the batcher went down for longer than the sequencing window period. And that would probably cause a reorg pretty similar in size to like the batch submission window. So that'd be a really large reorg. We don't really expect that to happen because we can kind of really harden the batch submitter and make it work. The other case is when L1 reorgs, and there's kind of two specific things there. The first is these L1 origins we refer to by number in block hash. So if you refer to an L1 origin that then reorgs, you have to reorg your L2 chain around that. So we're going to set a confirmation depth to kind of build the chain. You're allowed to do that through the sequencer drift because you can use a slightly old L1 origin. So with that, we don't really expect many reorgs there. And then the last thing is like if L1 reorged and like reorged out a batch, but like we expect, like when you reorg L1, the transaction does get re-included, so it would probably just like find the same batch again. So it's a long-winded saying like very rarely, and we're tuning parameters to make them even less likely. Cool. More questions? So now this is kind of very lowest level details of like, we have these batches, how do we actually put them on chain? So we use the timestamp of the block number, the epoch or L1 origin, and then we actually strip out the deposits from the batch data because the deposits are already on L1, we don't need to re-include them. And then basically just take the data, turn it into bytes, stuff them together with a bunch of other batches, compress them all, and then split it up over L1 transactions to kind of be maximally efficient. And there's some like more anti-DOS stuff in here, so you always have to have it. And then here's basically the diagram. The point is basically it's one more step that we're doing to lower kind of the data availability fees, and kind of just maximally efficiently use L1 transactions. So this diagram is actually from our specs repo. So if you're interested, I could talk about it more later or like kind of walk you through it then. So it's a bear of a diagram.
It's for ants.
Pardon?
It's for ants. It's supposed to create.
Yeah. So yeah, if you want to see it, it's in the specs of the Optimism mono repo. That's kind of the best place to find like more of the nitty gritty details. Yeah, it's just something we're doing. So take more questions. Cool. Guys, taking a step back, walking through some of the differences between kind of the current system and Bedrock. So we're gonna have again fixed L2 block time, targeting 2 seconds. CTC contract and the SCC contract are gone. We just submit batch data directly to like an address on L1. We're not doing any EVM computation over the data that we're submitting. Yeah, we have L2 reorgs working hard to make sure they don't happen. Can handle L1 reorgs a lot easier. We're gonna have snap sync. It's gonna be a lot easier to upgrade. We got P2B stuff, and kind of we went through the mechanisms where deposits are much more live. Yep, talked about the specs. The code's all in the Optimism mono repo. There's the OP node, there's the OP batcher, and there's the proposer. And then kind of as this gets closer to being more public and like getting to DevNet, testnets, we'll have an upgrade guide, some high-level docs. Right now we're at the DevNet phase. If you're really interested later, you can go do this exercise. It's up. And we're kind of working on the stability there. And then kind of over the rest of the summer and this year, we'll get kind of like partner DevNets, get like a public test net, and then migrate towards the end of the year. Yeah, so take questions. That's pretty much all I have. Yeah.
We mentioned, blocks and set blocks. We talked about the bots or the verifier, but the question is where does the protocol window fits in that? Like, for example, in my mind, we would have finalization after the protocol because it's the only way we're certain that the data will not change, the state will not change.
Yes. So this is where it gets interesting. So the fault proof is really for the output proposal. So the fault proof is like, the output proposal is basically the communication back from L2 to L1. So you can kind of actually imagine a world where you don't have that bridge back. This is like, it's a little kind of trappy, but you can like, you basically, the source of truth is what your verifier says. So we don't really have a mechanism to like revert a faulty transaction from a batch. We don't like modify the batch and what's been submitted during a fault proof. What the fault proof stops is kind of like a fake transaction that says, send all of the money to this person. And then if the batcher then does submit like a faulty transaction or a transaction that's not valid, it's the rollup node in the execution engine that refuses to execute that transaction.
Except if the full node is malicious. It's malicious itself, right? In a decentralized future where the sequencer might be malicious.
Yeah, so you're relying on the verifiers as full nodes in the network. No. Pardon?
It was finalization of layer 2 data work.
Yes. How does finalization of layer 2 data work? Kind of when you're confident that it's never going to be reorged on L1.
Are you looking at the epoch level or are you like the slot level on layer 1? Like, I assume layer 1 here means the state layer 1, and then you should be like doing per slot. You can assume like crypto economically
Right. We'll probably, so what exactly we'll use for the finalization period, we'll probably just use like the finalized head. We use a lot like unsafe, safe, and finalized head kind of internally because we know that API well. So the finalized head is what will get tracked over to the finalized head on the L2 execution engine.
I guess I have another question. Like, how bad is the L1 reorg in this context? Suppose you have a single slot reorg versus a multi-slot reorg.
How bad is a reorg? Not that bad. I mean, so whenever you get like a reorg, you just like dump out all the transactions and like they just get moved over to the new chain. And you just kind of rebuild the new chain with with a very similar set of transactions. So it's like a little annoying, but like your transaction's probably going to get included. And if it didn't get included in the same chain, it's still in the mempool. Like, yeah. So it's like not great to see, but it's not going to be, especially with like a short L1 reorg, it's like, it's deeper on L2 because we have multiple blocks per L1, but it's not going to be a huge chunk of time.
And I assume you also recompress all the data again with the new data as well.
Yes, yes. If there's a reorg and we have new L2 blocks, we have to resubmit those blocks.
Can you talk a little bit about, I guess, the fixed 2-second block time, like why that was chosen, like why it really fixed?
Yeah. So for the fixed block time, 2 seconds is kind of the plan. And that's just kind of looking at like, we want to have a short block time because that's a good user experience versus what can we sustain. And so 2 seconds in that range was where we landed as like, we think we can get this and it's still going to be a good user experience. So that's not quite final, but that's the plan and we'll be testing that. Yep. Any more questions? No? That's it for me. Thanks for coming, everyone. Yeah, I have a blurb. Cool.